Back to presents. Ooh, sorry, I clicked out of it. There we go.
Very good. Are we recording, Stephen?
Yes.
Okay, perfect. Thanks. Appreciate it. So hello, everyone. Welcome to today's webinar. Thanks for being here. My name is Katie Brickey, and I'm the current chair of the American Society for Quality's Chemical and Process Industries Division. The mission of the Chemical and Process Industries Division is to facilitate the interchange of ideas, tools, practices, and solutions necessary to address real chemical and process industry problems. And to that end, today we are excited to host Dr. Annie Booth, who will present her award-winning talk titled Contour Location with Deep Gaussian Process Surrogates. Annie's talk today was awarded the Schewel Award for the best presentation at the 2023 Fall Technical Conference. And today's webinar is co-presented by the 4 divisions that sponsor the Fall Technical Conference. So we want to say congratulations, Annie, on this award, and thank you for being here today. Before we begin, I'd also like to take a moment to thank Stephen Barnett, our webinar chair, for all of his behind-the-scenes hard work to orchestrate this webinar and all of our webinars this year. So thank you, Stephen. And now I would like to introduce our speaker today, Dr. Annie Booth. So Annie is an assistant professor in the Department of Statistics at North Carolina State University. She specializes in surrogate modeling of computer experiments, including uncertainty quantification, active learning, Bayesian optimization, reliability analysis, and digital twins. She graduated with her PhD in statistics from Virginia Tech in 2023, go Hokies, and her dissertation focused on the development of Bayesian deep Gaussian process surrogates. On a personal note, I'll say I first came to know Annie when she was in graduate school, and I was her mentor for a summer internship. Even at that early stage in her education, Annie was already way smarter than me. But I've always admired her humility and her humor. Annie is a really fun statistician and person to be around, and so we are delighted to welcome her here today for an encore presentation of this award-winning talk. So Annie has let me know that you can submit questions in the chat feature in WebEx, and we'll monitor those, and she can address them during the presentation if you have questions, or at the end if you'd prefer to wait. And so with that, I hand the floor over to you, Annie.
Great. Thank you, Katie. It was a while back when we first met, but that internship launched like my whole career.
There you go. I'm responsible.
In design of experiments, right?
Yeah.
So thank you, Katie and Stephen and everyone for attending. This is work that I completed as starting in my graduate studies. It's part of my dissertation with my advisor, Bobby Gramercy. And this project continued kind of as we are, wrapping it up and expanding it. So I have actually added to the title reliability analysis just because I want to make sure I connect this to the future and the work that came after and where this is going. This is also joint work with Ashwin, who is an aerospace engineer at Penn State. And I'm going to be talking about deep Gaussian process surrogates for contour location, which is the main theme of my talk today. But I also want to comment on how that will extend into reliability analysis. So if none of those words mean anything to you at all, do not worry. I'm going to walk you through all the pieces of it. And before I get started, I do still need to comment. I was previously named Annie Sauer. And so some of the works and references throughout will have my maiden name on there. And I got married, I guess, just over a year ago and changed my last name. So I'm now Annie S. Booth. And so both of those are me. Just FYI, as we're going through, those are both my works. Hopefully is not that confusing. And every year that goes by, it gets easier. So where are we going today? Oops. I want to motivate this work by focusing on one particular problem, which is still kind of broad reaching, which is that we'd like to, in general, design better things, aircraft, cars, satellite, any type of thing that we use in our day-to-day lives that are particularly based on these kind of fluid dynamic simulations. So for now, we're thinking mostly of things that are moving through the air, right? And so we want to build better things that can move through the air in better ways, which is why we work so closely with aerospace engineers. But we are working on specifically a simulation of an airplane wing. So I've got this figure down here in the left. We are going to be simulating basically as air comes through what happens with the shape of the wing as we change different parameters and different environmental settings of it. The big obstacles to designing better things, better wings, better cars, all of that, is that we can't experiment with these things directly. Naturally, we can't make a whole bunch of different airplane wings, attach them to airplanes, and throw them up in the air and see which one is best, which one is safest, which one is most efficient. Like, I hope we can all see pretty easily that we can't do that. The other thing that is important when we're trying to design things that are better is that we need to keep better within the realm of safety and regulation. So we may want, what's the wing that flies the fastest, but we always have these other kind of regulations that, well, we can't just have the one that flies the absolute fastest. It has to be mandated that it's fast, but it also has to meet efficiency for things like environmental regulations, fuel consumption. It also has to meet safety regulations. Safety regulations are a really big deal. So we're not just looking to kind of optimize things, but we're really looking to do a two-stage problem of optimizing things only given that they meet these certain standards. So how do we solve these two challenges? Well, I have foreshadowed the first one. We solve this kind of problem of not being able to directly experiment with things by simulating them. As I've already said, we're working with engineers who know a lot about computational fluid dynamics, and they can simulate how airflow moves around these things. And we address these kind of meeting regulations in reliability analysis. So in this realm, we are looking at making sure we can quantify failure probabilities and keep those really, really low. So this is kind of a two-stage problem, optimizing given that you have satisfied these reliability constraints. For today's talk, and we're going to only focus on kind of this first part. How can we make sure that we satisfy these reliability constraints? Expanding that into optimization is the topic of future research. But this is what we want to do. We want to use simulations to make sure that the things we're working on meet these requirements for safety, efficiency, and so on. In particular, we're going to work with one computer experiment or computer simulation. It is simulating airflow around an airfoil, which is just a aerospace engineer term for something that moves through the air. In this case, this is our airplane wing. Specifically, it's called this RAE 2822 wing. This simulation is actually publicly available. So this link here, the code is all available on GitHub. It's free for public use. And we have taken from this repository kind of a limited example where we have specified only 7 input configurations. So there are 4 parameters that control the shape of this wing. And these 4 parameters really work to kind of design like a mesh, which I'm showing you in this right panel, that's going to specify the shape. And then we're controlling some environmental parameters like the angle that the wing is flying at, how fast it's flying at, and then we have Reynolds number, which is kind of a parameter that controls some of the fluid flow properties. And you can look at a bunch of different response values for these types of simulations. We are focused on the lift over drag ratio, which is a measure of flight efficiency. So lift and drag are some of the, lift is how much air, basically air that the plane is getting, and drag is how much resistance it's getting as it goes. So in order for this to be efficient, we don't want this ratio to be small. Okay, but we have this simulation, and our goal is to turn this into something actionable. Specifically, we're going to focus on identifying which input configurations, so these design and flight conditions, are efficient enough. So they have a satisfactory lift over drag ratio. That is our goal. The tricky part here is that we can't just run every single input configuration that possibly exists. This is like a 7-dimensional input space on a continuum. We can't just run them all and, just see, oh, well, which ones had a satisfactory LD ratio, because this computer experiment is expensive. It's not trivial to run. We can run it on a supercomputer. We can use parallel cores. I think the fastest we've got it to go is maybe 5 minutes for a single input, but these things that requires a lot of parallel cores. And naturally, that limits us to, hundreds or maybe thousands of runs, but not too many that we can do in a reasonable amount of time. as we develop our methods to work with limited data, we will also be able to conquer experiments that are more expensive. So if we had this mesh for this airfoil and we made the mesh denser, we would get finer resolution on our simulations, but it would be a lot slower. So I will say the version of this simulator we're working with now, we can get it to run in like 5 to 10 minutes. But our target is to then later on work with a denser mesh, which is slower, but get just as good results, even though with a slower experiment, we won't be able to collect as much data. So learning the most that we can from a limited amount of data is the name of the game. Which brings me to our particular objective in this case. What do I mean by learning the most? Well, for our application, we are looking to identify passes from failures. So the most learning that we can get is if we could successfully identify every single response for every single input as either acceptable efficiency or unacceptable efficiency. So I'm going to call that a pass and a failure, which really boils down to learning the contour in this response surface that separates our passable region from our failure region. If we can learn that, then we can expand our methodology to identify actual failure probability. So what is the probability that our flight is inefficient enough or exhibits failure behavior? So that's where we're going. But for now, we're just trying to learn the contour. So we're taking it piece by piece. Can't tackle huge problems all at once, right? We got to go in little steps. So that's our objective. Try to find this contour. Since our experiment is expensive, we need to use a surrogate model. So a surrogate is this meta model or the statistical model of a computer simulation, which is itself a model of the real world. So that's where this meta model idea comes in. The surrogate is trained on the limited data we get from the actual experiment, and we use the surrogate to get predictions with uncertainty quantification so that we can predict or make decisions on input configurations that we haven't had the chance to run through our actual computer model. Surrogates are useful for downstream tasks, reliability analysis, which is what we want to get to in this application, Bayesian optimization, which is also something that we want to get to eventually, calibration, sensitivity analysis, you name it. And these models are more important the less data that you have. So quick side note, if you have not seen Bobby's textbook, Bobby wrote a really nice textbook all about surrogate modeling with Gaussian processes, and he graciously posted it online for free. So you can look up this resource. It's online and it has code. It has all kinds of reproducible examples. I highly recommend it. If after this talk you're like, wow, I'm really intrigued by this area of research, that's the first thing that you should go to. Okay, so we need a surrogate model that can do a couple things. It needs to be nonlinear because our computer experiments exhibit these nonlinear surfaces. We want it to be non-parametric, at least as much as we can, and we really need accurate, efficient predictions with really good uncertainty quantification. So we're going to use a Gaussian process. If you haven't seen this before, it boils down to assuming a multivariate normal distribution over your response. As a prior distribution, we're just going to use a zero mean, and we put all of the kind of work of the model into this covariance matrix, which is a function of input locations, and it outputs the covariance in the response between those two locations. So covariance is going to decay as your locations get further apart. So naturally, the response of locations that are close together should be more correlated with each other. And as you get far apart, those might not have as much pull or impact on the response that you observe at those far apart locations. There are different ways to hyperparameterize this kernel. This K function here can be a Matern kernel, it could be a squared exponential kernel, it can be any positive definite kernel. And I've just highlighted them in blue some hyperparameters, which we don't necessarily, you can do different things with these hyperparameters. I'll touch on it in a second, but I'm not really going to focus on them. The idea is that I want to show you how powerful these models can be. So let's focus on this plot on the right. And let's pretend that these red points are data observations you have gotten from a toy computer simulation. You put in each of these X locations and we observed out of our black box, we observed these Y data points. We want to fit a model to this so that we can predict the whole surface of this function, not just at those points that we observed. So the Gaussian process conditions on observed data, and then your prior distribution turns linear distribution, and in a GP, our posterior predictions are also Gaussian, and they have this nice closed form solution that relies on this covariance kernel. You can use whatever you want to do to estimate those hyperparameters that you don't know. Oftentimes people will do maximum likelihood, or you can sample them with MCMC. That is not the subject of this talk, but presume that you've got some kind of good hyperparameters and you observe sample data, we can get a fit that looks like this. So I've got a posterior prediction, which is the dashed line, and then I have these 95% uncertainty bounds, which are this kind of blue region. Hopefully you can see from this example that this is doing a pretty good job at providing a non-linear fit to this data. It is providing UQ, which is kind of helpful, but also not ideal, because if you zoom in on the right portion of this surface, you can see pretty easily, because this is a one-dimensional function, that this is really a piecewise function. There's this non-linearity going on the left, but then it's just a straight linear function on the right. We are assuming, by the way, for these examples, that we do not have any noise in our data, because most of our computer simulations are deterministic, or if they have a small amount of noise, it's small. So knowing that there's no noise in this data, we can clearly see that it's linear on the right portion, but our Gaussian process is overinflating the variance in that region of the space. This is a byproduct of stationarity. So here's the true function that our data came from. Here's our GP fit. I want to foreshadow what you saw in the title of my talk, which is a deep Gaussian process. So here's a fit that I haven't told you about deep GPs yet, but this is what a two-layer deep GP looks like when fit to this data. It matches the nonlinear flexibility on the left portion of the space that our regular GP had, but it is much better able to adapt to the linear portion on the right. So it's not overinflating the UQ over here. So I would argue that this is a much better fit than our shallow GP, which was forced to be stationary, which is a byproduct of that kernel really only being a function of Euclidean distances. There are other ways to address non-stationarity or to build this non-stationary flexibility into your surrogate model. One of the things you can do is adapt the kernel so that it's not just a function of Euclidean distance. This is popular in spatial statistics, harder to do in higher dimensions. Another thing you can do is do a tree partition Gaussian process or a local Gaussian process. These are things that my PhD advisor Bobby had worked on in the past. Both of these bring in additional flexibility to a regular GP, but they give up the global learning that you can obtain if you have one global model. So they end up, kind of cutting up the space, fitting different models on different parts of it. So the big downside to those that we wanted to kind of circumvent was this locality. So we want a model that is flexible enough to handle non-stationary, non-linear surface, can provide good UQ, but can also be global all at the same time. So we're going to embrace a deep Gaussian process, which actually has origins in spatial statistics too, as spatial warpings, but it became popular, I guess, just over 10 years ago when some people in machine learning caught onto it and showed that these things have, very good predictive power. So what is a deep Gaussian process specifically? It is just a functional composition of regular GPs. That's it. So here in this plot, I'm showing you a linear or an evenly spaced one-dimensional vector of X locations that I have plugged into a Gaussian process in order to get Y1. So this is just a nice, smooth, random draw from a GP. If I take those Y1 values and I plug them into another GP, now I can look at X to Y2, which was composed by two Gaussian processes, one on top of the other. And now this is what we call a two-layer deep Gaussian process. And you can keep going, you can add layers, as many as you want, although for this talk, I'm just gonna focus on two. And what's happening by this latent variable, this Y1, if I ignore it and I'm just looking at X to Y2, Y1 is really accomplishing a spatial warping. All that it's doing, if you look in this first panel, is it's stretching the inputs near the middle of the x's. So that positive slope in the middle is like a stretching effect. And these flatter slopes on the edges are like a squishing or compressing effect. So in the middle panel on this color gradient, I'm actually showing you the distribution of Y1 as it relates to X. So it has stretched out the middle and it has squished the edges. In this very simple example, we're not getting very complicated functions out of these different warpings, but you could. And the idea is that if we turn this into a prior distribution, then we can get posterior predictions that are more flexible. So this is just like simulating random draws from a deep GP by composing regular GPs. But let's turn this into an actual modeling scenario. So we presume that we observed inputs X and we observed response Y from our black box model. Now I'm going to place a deep GP prior on my data by assuming that there is some W. Previously, this was our Y1. This is this latent variable, but I'm calling it W now because I want you to think about it as a warping. So X goes to W as a Gaussian process, and then W's go into Y as a Gaussian process. But we only get to observe X and Y. We don't see W. So we want this additional flexibility from this warping, but we don't know a priori what this warping should be. So we want to do posterior inference where we integrate out this unknown W, but this integral is not possible to do directly. So what can we do? Well, we can approximate this posterior doing something like variational inference. Later, I'm going to show you a plot where I compare to, I think, the most cutting edge implementation of this deep Gaussian process variational inference, which comes from this Salimbeni and Diesenroth paper called DSVI. So I will compare it to some software that does this variational inference. The idea there is just to kind of approximate the posterior with the closest version from some target family where you actually can solve it. The thing that we're going to embrace is the MCMC posterior sampling. So we're going to sample this W, which is this unknown variable, this unknown latent function. And by doing this kind of full sampling of this, we end up getting, I think, higher fidelity models, which I will hopefully convince you of when I show you some predictive results. And we get more thorough uncertainty quantification, which is going to be important when we transition to our, contour location, reliability analysis, all of those old objectives. So we're going to use elliptical slice sampling of this latent W. In my software, I've built in Metropolis Hastings sampling of these other hyperparameters in the kernel, but that choice really is not super impactful. There are other alternative softwares that do like optimization type things for those. The ESS of the W is the key. So I have a quick diagram of what ESS looks like. I don't want you to get too lost in the weeds on this. The key part of this MCMC algorithm is that you sample from a Gaussian process prior, which is a nice smooth function, and then you propose the whole function all at once. So we're proposing our previous iteration, which is the whole functional surface in some kind of weighted average with this prior draw. So we don't have to do little kind of tweaks of little parts of the function all at once. We can actually get proposals of the whole warping space all at once. And our probability of acceptance is just based on a Gaussian likelihood ratio. So each piece of this algorithm is really basic, but when they all come together, they give us really efficient mixing and really great samples. So in this one-dimensional example I've shown you before, I have put together this R package, which you can catch up on CRAN. It's called Deep GP. We can do functions that are just like this. Fit2 layer is going to do all of this elliptical slice sampling for our observed X and Y. Then you can use the trim function to cut off burn-in and thin your samples if you want. And then I have built in this S3 class predict function to get predicted means and variances at any X locations that you want to predict at. So that's how I got this fit from that panel that I showed you before. Now in the bottom right, I'm showing you each gray line here is one elliptical slice sample of that warping that was learned from these red data points. Each gray line but has a slope at the start, whether it goes down or up, it doesn't matter. That slope is still accomplishing a stretching for the X's in the left of the space, and then that slope flattens out on the right. So it's stretching the X's in the left and it's squishing the X's in the right, and that's what's accommodating this model's ability to fit this nonlinearity on the left and to fit this linear portion on the right. It's this warping of the X's. So I have a bigger example in 2 dimensions. In 1 dimension, each sample is just a line so we can see what they look like. In 2 dimensions, we actually have a 2-dimensional warping. And so here's a function called the G function. And in the middle panels, I'm showing you one, you can think of it as a node, kind of in the neural network nomenclature. This left plot here in the center is one node of my latent layer, and the right is another node of my latent layer. So my W is really 2 dimensions. So if I look at each one of them separately, they're just a conditional Gaussian process. This is a nice, smooth, pretty simple surface. But when I put those two panels together, I can see on this very rightmost panel how together they are warping my inputs. So I start with an evenly gridded X, and I learned from this ESS that I want to take those and I want to kind of stretch them along the diagonals and then fit a Gaussian process on that warped, stretched version, and it will predict better the surface, which I want to predict, which is in the left panel. So to convince you of this, I did a bake-off. I bumped that function up into 4 dimensions to make it a little harder. I ran our DGP with elliptical slice sampling, and that is in the green. I'm showing you RMSE, so lower is better. I'm showing you continuous rank probability score as well. Lower is better on that, and that just incorporates some uncertainty quantification. And compare that to a stationary Gaussian process just with MLE for the hyperparameters, and we are like knocking it out of the park on this one. For this complicated surface with its stiff peaks and ridges in the bottom part, no matter what sample size we tried, 3,000, 5,000, 7,000, we were able to get continuously improved accuracy and better uncertainty quantification with the flexible deep Gaussian process compared to the traditional stationary GP. So let's circle back now to our motivating simulation. We have 7 input dimensions. We have this airfoil, and we're looking at the lift over drag ratio of the response. So if we started with just a static space filling design, so I started with a Latin hypercube sample and I just spread out 500 points in those 7 dimensions. And then I fit a deep Gaussian process on those data points because we suspect that there's some kind of non-stationarity going on in this airfoil as it moves through the air. We compared that to a stationary Gaussian process, just like I showed you. So the green here is looking at RMSE performance and CRPS performance from our deep Gaussian process. Both of those are outperforming the stationary Gaussian process just on a space filling design. And then as I promised, I did try out the Python package that does this variational inference implementation of the DGP, and just with this default parameterizations, it was not doing very well. So in general, that software I think requires a lot of fine tuning in order to get it to work, and just out of the box, it's not performing great. But I do have that as a competitor because I promised I would show you, the alternative versions of this. Okay, so we're getting better predictions, but that was not our goal. Do you remember our goal? Our goal was not to predict better over the whole space. Our goal was to identify the failure contour so that we can separate passes and failures. So I've defined a lift over drag ratio of 3 as the cutoff. Any ratio less than that is failure, inefficient, can't do it, right? Anything above that is okay. So if I use these same designs, I already showed you these left 2 panels, but now I look at sensitivity and specificity just for predicting failures. Our deep model is outperforming the stationary Gaussian process. It's better at picking up on which inputs are failures and which ones are not. So this is getting closer to our objective, but it's still not great. Like there's still room for improvements. We can totally do better if our goal is just to find that failure contour. And the way we can do better is by designing our data. Here's that design of experiments that I started with my Eastman roots like many, many years ago. We can design our computer experiment sequentially to target the thing that we want it to do. And in this case, we want it to learn a contour in the response surface. So we can start with a small design, like a small LHS. Is that Ashley? I was gonna say Ashley sent a heart. Shout out to Ashley. She was at Eastman too. Okay, then we can fit our surrogate model to it, and we use our surrogate to inform which input we should run next through our black box model so that we can learn exactly what we want to learn, which is where's the contour, right? And then we run our simulator, we get our data, and we do this in a big loop. So we're collecting our data sequentially to target our specific objective. That will allow us to do better on that objective than if we just randomly spread out our data in the beginning, right? So to choose this next input location, this upper right box here actually involves solving some acquisition function. It's really, we're trying to optimize some objective criteria that tells us which inputs will give us the most bang for our buck, right? In a deep Gaussian process, it's really hard to do some kind of stochastic numerical optimization because your surrogate model is itself pretty hefty. So we're going to use candidates in this space. We're going to spread out some candidate locations that we haven't observed yet through our model. And we're going to use some criteria to tell us which one of those has the highest utility for learning this contour. And then we're going to run that one. We're going to choose that as our xn plus 1. So a quick illustrative example to kind of motivate these last developments I'm going to bring up. I have used this function here. It's a two-dimensional function, and I'm calling it the plateau function because it has two flat plateaus with this sloping region in between them. And this upper right surface plot, I've rotated it a little bit so that you can see what this surface looks like. But now I'm showing you in the heat maps, the high flat part is in the lower left. So I collected 15 random points spread throughout this space, and I observed the response at those locations, and then I fit my DGP surrogate to those locations. I'm showing you in the heat maps now what my predicted mean surface from my DGP is. The blue line is the true failure contour, which I have just hypothetically for this example put right in the middle of the slope. The black dashed line is where my surrogate is predicting the contour is, just based off the limited data it has access to as of now. And then in the middle panel, I'm showing you my uncertainty from that surrogate. Yellow or white is the highest, red is the lowest. So I have low uncertainty in my flat regions where I've observed data points. I have higher uncertainty where I haven't observed data around the contour, but I also have high uncertainty around the edges where I just have no data at all. In the right panel, I am showing you the entropy, which is calculated from these other two panels. So entropy just takes the probability of our pass or our fail. So it's somewhere between 0 and 1. What is our fail probability at any location? And it plugs it into this formula, which is like the probability times the log minus the negative version of that. You can look it up if you aren't very familiar with it. But all that it does is it plugs into this function that is the highest where your probability is 50-50. And entropy is really low if you have like 100% probability of failing or 100% probability of passing. It's highest around that 50-50 uncertainty. So it's just a function that tries to quantify your uncertainty in whether you're predicting a pass or a fail. And now, if you look at this panel, you can see that entropy is really high around our predicted contour. It's a little bit high over in the corners where I don't have data, but compared to the middle panel, there's not the same level of like highness that is happening on the outsides because it doesn't really think there's a contour there. Entropy is high where it thinks there's a contour. Okay, so that is enough setup of this toy example. If we wanted to use this data and use this surrogate to tell us which input should we run next through our black box model so that we get the best learning of the contour. Like we don't have this blue line nailed down yet, right? Like we are off. We need to fix our predictions. We need some more data. Where would you put that next data point? Well, what people have done so far is they say, well, I'm going to put my next data point where entropy is the highest. That's where my uncertainty in whether I'm a pass or a fail is the highest. So that would be anywhere along this predicted contour, anywhere along this ridge. This is like, there's a whole body of literature on methods that use entropy as their acquisition function. So put your next point at the highest entropy location. This requires some kind of numerical optimization, which is really tricky for us with our deep Gaussian process. So we have kind of two problems here, and I'm going to show you the two problems. But if we just try to put our next point where there is the highest entropy, we're going to hit two major obstacles or two major pitfalls. The first one is that if we don't do some kind of multi-start numerical optimization and we just spread some candidates out in the space, there's almost zero chance, I mean, there's a really small chance that we would actually end up with a candidate on this contour because this contour is super peaky. Entropy is like flat so much of the space, and then there's all of a sudden these really big peaks. If we just have some candidates and we spread them out, we're probably going to miss. We're probably going to end up with all our candidates in the red region, and then we have no information to go off of. Then we're just like, well, shoot, none of those have high entropy. Let's just pick one at random, and we're back where we started, right? So with our deep Gaussian process, which we want to use because it gives us better predictions, especially in our motivating application, we can't do this numerical optimization. The second pitfall here is that just entropy on its own does not promote enough exploration, right? Entropy is peaky around this predicted contour, but there's there's maybe like there's local optima over in these corners, but if we're only ever trying to maximize entropy, we would miss out on exploring this whole right part of the space. And what if there was a disjoint failure region over there? We would never see it. Entropy just clusters way too much around where it thinks the contour is, and it doesn't explore enough. So we have proposed two methods that get around these two obstacles. And for the sake of time, I'm not going to go too much into the details of these two things, but we're going to get around this numerical optimization problem by not just placing candidates randomly, but placing candidates very strategically. That's the first thing. Then we're going to get around this not exploring enough problem by not relying on only entropy. We're going to combine entropy with our uncertainty into kind of a new joint acquisition. So those are our two contributions that are going to allow us to do this contour location with our deep Gaussian process. So how do we strategically place candidates? Well, we do this thing called triangulation of our existing design. This is in another paper that I encourage you to check out if you're interested. But the idea is that don't just put your points randomly out there, but actually do a triangulation of where you've already observed data, which is these open circles in this plot, and then put your candidates like in the center of those triangles. So each of these red diamonds here is where I would put a candidate. There's a lot more details that go into this, but in the end, this ends up spreading candidates out from where you already have data, right? So it's trying to infill the holes where you have not yet observed data. So we call these tricans, and it's just strategically spreading out your candidates from the data points you already have. So that's the first thing we're going to do. We're going to say, okay, well, propose some tricans. Then on those locations, we're going to calculate entropy and we're going to calculate uncertainty. So I've shown you this entropy plot before. The purple points now are where my tricans candidates are, right? You'll notice that I got candidates really close to where my entropy is high. And I also got candidates kind of on this outside where I have high uncertainty areas. If I just pick the candidates with the candidate with highest entropy, I'd probably end up with just this triangle one down here. It looks like that is the one of my candidates that has highest entropy. But I'm not going to do that because I want to make sure I'm exploring as we go throughout this loop and we repeat this process over and over. So we're actually going to look at the entropy of those locations and look at that predictive standard deviation, which was that middle panel I showed you when I first introduced this function. And we're going to pick points on the Pareto front of these two things. So we want high entropy, but we also want to put points where we have high uncertainty. And ideally, we want to put a point where there's both. If there's both of those, we would like that. So now the purple triangles are those candidates that are on this kind of Pareto front. They're not dominated on any or by any other point with regards to entropy and uncertainty. And on the plot in the middle, you can see where these purple triangles are. They are in areas of high entropy, but I also got one over here where I have high uncertainty. So we propose just randomly, if there's multiple points on the Pareto front, just pick one at random. And then as you go through this feedback loop over and over, you will end up learning where the contour is, exploiting, and also making sure you explore the whole space. So altogether, I took that plateau function, I bumped it up to 5 dimensions to make it harder. I started with 20 points, and then I did 120 sequential acquisitions following our method. The green line here is our deep Gaussian process with those Pareto front tricans acquisitions. And we looked at sensitivity in terms of classifying failures, and it outperformed the stationary GP with the exact same method. So the green and the orange, the only difference is the model deep. But it also outperformed the stationary GP with the state-of-the-art just optimizing entropy. On the right, I'm just showing you the result at the end of this design. So at 150 points, this is my sensitivity for our methods. Our proposed method is the green one. And I'm also showing you results from a static space-filling design of the same size. So the sequential design is important. All of our sequential designs are outperforming their stationary kind of just space-filling counterparts. But having the right flexible deep model is also very important. It's outperforming all of the stationary shallow Gaussian process models. And it's also like avoiding this pitfall that occasionally happens with the blue competitor here, which just optimizes entropy, occasionally did terrible. These ones that go off the plot that are occasionally terrible, happened when all of our acquisitions were just kind of clustered up all together, where entropy was high and it just kind of put points all together in a big cluster and it didn't explore. So the Pareto front combination of uncertainty and entropy is hugely important at avoiding these clustered acquisitions and avoiding this trap where your sequential design might actually screw you compared to just space filling, which did happen occasionally with only the entropy. I have a two-dimensional example, which is in our paper if you want to refer to it. I will just skip this for now and go to our final results on our motivating application. So remember this airfoil with these 7-dimensional inputs, and we wanted to identify passes and failures. I previously showed you these static LHS results, the green and the blue, where I showed you sensitivity and specificity for a 500 point Latin hypercube sample. And I showed you the deep model did perform a little better than the shallow model. So you've seen those before. Now the takeaway that I want to show you is that we did a sequential design with our tricans, Pareto front, deep Gaussian process surrogate, all of the 3 pieces that kind of make the magic sauce here. We started with 100 points spread out, and then we did 400 acquisitions. Each green line here is the performance of one of those sequential designs. And the key takeaway is that these sequentially designed experiments can outperform the static ones with less data. So our sequential, even across Monte Carlo repetitions with re-randomized starting designs, we're getting better performance in sensitivity with only 300 data points than we got with 500 space filling points. So to circle back around, with the right surrogate and the right design method, you can get better learning from less data, which is going to be really important when we expand to even more expensive computer experiments. Now, lastly, I want to leave off with this work, like Katie said, I presented last year at the Fall Technical Conference. So since then, I've followed up this with if we have a surrogate that has trained or it has been trained to learn a contour so it can identify where passes and failures are, how do you actually use that to estimate a failure probability? So how do you actually get to the reliability analysis part of it? And that is like a whole nother talk, but I just want to point you to, I do have a paper on arXiv, which is kind of a follow-up to this one. It's how do you do failure probability estimation with these GP-based surrogates, deep and shallow? And so I encourage you to check that out if you'd like. But everything, all my work and everything that you've seen today is in an R pack or is facilitated by an R package, which is on CRAN. And all of these examples, all of these figures are generated by code, which is publicly available on our Git repository. So I will stop here and open up the floor to questions at this time. Thank you all for your attention.
Thank you so much, Annie. Really appreciate your encore presentation of this really interesting talk. I attended in person and forgot a lot of the details, so I'm glad to have the chance to hear you present again with some updates.
Thanks, Katie.
Let's see, I don't think, Stephen, correct me if I'm wrong, I don't think I see any questions in the chat currently, but if you have any at this time, feel free to enter them now.
Cool. Oh, thank you. I do appreciate all of you for tuning in. And I do think Stephen mentioned I'm happy to provide my slides. I think he might even send those out. And all of these, if you're interested, there are a lot more details.
I think we might have lost Annie. Either that or I am lost. Stephen, can you still hear me?
Yes.
Okay.
I think it's on Annie.
Okay,
Yep.
perfect. I thought it was Annie having a problem, but for a second there, you
You
don't
never know.
if you're freezing or if they're freezing. Very good. I'm sure
Yeah.
she'll join us in just a minute. We had one attendee send us a message that just thanked Annie for her great presentation. I agree, very interesting work. If you do have questions, you can put them in the chat and maybe we'll ask them if she's able to join again in a minute. But Stephen, do you want to share sort of where
Oh, I think I'm back. I'm
Oh,
sorry. Can you hear
welcome
me?
back, Annie. Yeah, we can hear you.
Okay, I think my internet just flashed out. I am sorry about that.
Oh, You're fine. That's how it goes. I was just going to ask Stephen to share where the recording and slides can be found after this is over.
Yes. As part of your registration, you'll receive a follow-up email with links to the slides and the recording of the webinar.
Very good.
Should be
Cool.
straightforward.
Looks like we do have a few questions coming in. So we have one question, Annie. It says, what could be other applications where this simulation methodology could be used?
Ooh. So it is really broad. Most of my research concerns how do we model computer experiments, and computer experiments can be anything. So I work primarily with engineers, but anything that you can simulate. So I don't know, bridges, cars are the things that I work on more often, but the spread of diseases through populations, we simulate that. We can simulate population growth. We can simulate like there's some really cool stuff in like the biomedical realm where they're like simulating like medicines and all kinds of things like that. Anything that you can simulate, you're probably going to be asking yourself, well, I built this simulation, but now what do I do? Right? And that's where our statistical methodology comes in. Reliability analysis, failure probably but
We're losing you a little bit, Annie. Can you hear us?
The cost, those are some just off the top of my head.
We lost
Oh,
you a
the
little bit at the
economy,
very
that's a good one too.
we lost you a little bit there at the very end, Annie.
Oh, I am so sorry. Am I back now?
It's okay. You are back now.
I'm
So
so sorry.
no, it's not your fault.
Yeah, it's
Very good.
NC State's Wi-Fi.
Yeah, yeah. Very good. Okay, there's one other question about how do you report these results to non-engineers? So when you're sharing out some of
Non-engineers.
these learnings or these conclusions,
Oof.
perhaps to decision makers who are non-technical.
So I think there's multiple parts to this. First, when I am working with engineers, engineers are pretty smart. Like in general. I have found that the ones I have worked with are interested and intrigued and actually learning a lot of the details of this. So there's a back and forth. I need to understand enough about the process that they have expertise in to, make appropriate modeling decisions. And they need to understand enough about how the models work to feel confident in the decisions that we are making. So in the end, I think it boils down to pinpointing what they want to learn and then showing them that you have actually learned it, which sounds crazy, or it sounds like circular reasoning, but I can show you. If you tell me I want the minimum value out of my computer experiment, well, I mean, there's this concrete evidence. I will say, okay, run these points and you can see what values you got out of it. So it's almost really easy to show them when you can say, I think this is the best answer. Just run this through your model and they actually get a good answer. But it is a little tricky. It's definitely about communicating confidence in what you're doing. At the same time, making sure you understand enough about the other side too. That's a
Very good.
loaded answer.
No, yeah, it's a conversation, right? A two-way conversation, not just explaining the statistics, but understanding the science, understanding the statistics, both of them. Very good. I don't see any other questions yet. Do you, Stephen? Am I missing anything?
No, that's all the questions I see. But Annie, I actually did have a question for you.
Ooh, go for it.
If you can go back to your slide on kind of the results from your motivating example. Yeah, that one, I think. So here you plot the sensitivity as you do your sequential design for your DGP. What do the lines look like when you just use your GP MLE estimates with the Pareto front? I imagine that it doesn't go up as fast, or there's definitely a difference, but
So That is a really good question. And my answer is I didn't run it. Because this model takes like it's not trivially fast and we had to run it on the supercomputer, I put the effort into running the DGP 10 times instead of running the other ones. I could do it, but here's what I think will happen. We were pretty confident based off of our static results with just the Latin hypercube that the deep Gaussian process is picking up on the some kind of non-stationarity. So we think that the deep model is important, right? If you fit the deep model on a surface that is stationary, it will give you similar performance. It should be matching. But we definitely saw a bump. So I think if we fit the Gaussian process here, it would be probably uniformly underneath the green lines. And if we didn't do our Pareto, like hybrid Pareto front, I think we would end up with clustered acquisitions, which would make some of the blue, if we plotted blue, some of them would shoot down. Just like we saw with like this previous example, I think we would end up with a couple that were like really bad. But that is just my guess. I haven't run it.
Yeah,
You
no,
can run
that
it
makes
if you
sense.
want. The code's out there.
Okay, I'll try it. I'll try
In
it
your
on my
spare
own.
time.
Good question, though.
Very good. With that, I think we will thank Annie so much for her time and her talk. Congratulations again on your recognition for this
Thank you.
work and this
Yeah.
presentation.
Honored to receive the award. This was a great opportunity.
Yeah, very good. We're honored to have you. Thank you all for joining today. We hope you have a good rest of the day and a good rest of the year. And stay tuned next year for some more webinars from CPID.
Great. Bye, everyone.